Hey guys, today we'll be going over the 2021 Special Exam 2, specifically question 4 from this exam. Um, this exam itself was actually considered to be one of the most difficult special exams ever created in the history of special in VCAA. And this question in particular, a lot of students had trouble with it. So today let's just go through it and let's just see what we can gain from this question and what ideas we can learn from it. Okay, so we can obviously see it's a vector calculus type of question. Um, yeah, so we have to sort of remember those concepts and sort of try and work with that. But let's see what we have to do first. Okay, so the first thing we need to do is we have to show that the path of the rear wheels of the car while in the air is given in the Cartesian form by y equals x tan theta minus 4.9 x squared on u squared cos squared theta. Okay, so just for context, what's happening here is there's a car that's performing a stunt on a track, and what happens is it takes off on this ramp here from B to O, and then afterwards it lands at point C and it continues downwards. Okay, but this I guess what's important here is this R of T thing here. This R of T thing is that bit here is only describing what happens to the car right after it takes off from point O and lands at point C or anywhere beyond point C. Okay, so after the car wheels, yeah, so until the car lands on the second section of track and starts again at point C. So that's what this equation here is describing. Okay, so let's go ahead and try part A out actually. So so the equation told us from above we know that um, x, right, is equal to ut times cosine of theta, right? That's what the x coordinate is going to be given by. It's going to be based on t, the initial velocity, and theta, which is the angle of takeoff. Next we have y. Y is given by ut sine theta minus half gt squared. Obviously, g is representing the acceleration due to gravity, and g is equal to 9.8 meters per second squared. Okay. Um, First thing is, obviously we want to get it in the form of y equals x. Y is in terms of x, so we want to isolate the t. We want to isolate the t variable and then replace all the t's in this equation here. Okay, so I'll do that with the equation of x in terms of t first. So what I can do is I can divide both sides by u cos theta. So I'll get t is equal to x, and since I divided both sides by u cos theta, I'll have u times the cosine of theta on the bottom, right? Okay, and then when I sub it into this equation here, when I sub this, what I have for t in terms of x, u, and cos theta into this equation here, what I'm going to get is y is equal to u times x on u cos theta times sine theta minus 1 on 2 g t squared would just be x squared on u squared cos squared theta. Okay. What do we notice from here? How can we simplify this? Well, the u's will cancel out. Sine on cos becomes tan, so that's what we get the first bit here. We just get x tan theta. Okay. The next thing here we see this half g term here, and since g is 9.8, half g is just 4.9. So we'll get that minus 4.9. The x squared's on the top, so 4.9 x squared on u squared cos squared theta, which is what we wanted to get, right? So successfully showed what we wanted to show. Okay, cool. Let's go to the next question. Theta is equal to 30 degrees. Find the minimum speed in meters per second that the car must reach at point O for the rear wheels to land on the second section of track. So for it to land at that point or anywhere beyond that point. So okay, let's see how we can do this one. There are two ways we can do this. Obviously, we have a parametric equation. So if I just rewrite that for you, the top here, r of t is equal to ut cos theta I plus ut sine theta minus half gt squared j, right? So we always have a parametric equation. Obviously what we did before was we made a Cartesian equation from the parametric equation. But now at this point, right, since we already have the Cartesian equation, we might as well just work with that because it's just easier to work with the Cartesian equation. So, I'll just, note that theta now is 30 degrees. So the angle of takeoff is now 30 degrees. So let's rewrite everything with the 30 degrees now accounted for. So what do we have? We have y is equal to, so originally we had tan theta x minus 4.9 x squared on u squared cos squared theta, which is what we wanted to show in the first place. So now if we replace f theta with 30 degrees, we're going to get y is equal to tan of 30 degrees times x minus 4.9 x squared on u squared cos of 30 degrees squared. Okay, that's going to become tan of 30 is root 3 on 3, so root 3 on 3x minus 4.9x squared on u squared. Cos 30 squared is going to be multiplied by root 3 on 2 squared. Okay, and then at this point, all we have to do, right? So just recall from the start of the question, C was actually so point C had coordinates 16, 4, right? So all we have to do here, right, is pretty much just sub in 4 for y and 16 for x, and then we can solve it on the CAS. So we'll go ahead and do that quickly. So if I sub that in, y now is equal to 4. I'm going to get 4 root 3 over 3 times, what's x? X is 16. So times 16 minus 4.9 x squared. X is 16. So 4.9 times 16 squared all over u squared times root 3 on 2 squared. Okay, then go ahead and solve this for our initial velocity, u, right? Because that's what we want to find. We want to find the minimum speed, right? Because obviously, when we solve this, what we get for u will be the minimum speed, right? Because that is exactly what it needs for the wheels to just touch the track at point C, right? Which is why we're solving for C equals at point C itself. Because that's why we're solving for point C itself. We could solve for anywhere beyond it, and yes, the car would still touch the track, but we want to solve for it to get to point C itself, which is the minimum speed, because what we're interested in is the minimum speed. So once we go ahead and solve this on the CAS, the answer we will end up getting is, just note that it has to be corrected 2 decimal places. So we'll get something like u is equal to 17.86, 98558, blah, blah, blah. We just have to round that down. Rounding it down, round it up in this case, 17.87 meters per second. Okay, so yeah, as you can see, it's not too bad. Part C is a little bit more difficult, but still not too bad really. So it says a ramp BO is constructed so that the angle theta can be varied, and for what values of theta and u will the path of the rear wheels of the car join up smoothly. So smoothly here is the key word. So it's the key word that we have to take into account. Okay. When you say it's smoothly, so just before we go on, let's just go back up to the diagram and let's think about what the word smoothly means, right? So the car takes off here, takes off on the ramp BO. It goes along this path from the origin to C, right? So the diagram actually explains this very well, right? You can see how the path of the rear wheels of the car, you can see how this dotted line ends up joining very, very smoothly with the ramp at the end, with this ramp from C to whatever this end bit here is, right? You can see how it joins up very smoothly. So what does the idea of smoothly means? It just means that the gradient of this path will match the gradient of this ramp at the end, right? So that's the only thing that we need to sort of take away from that word. And that's like, I guess that's the idea that will help us solve the question quite easily, actually. So what we know so far, right? We want to find the values of theta and we want to find the values of u, right? And yeah, so you need both of them to one decimal place. Okay, so let's go ahead and try and do this question. Um, what we can do first is we can we can sub in the values we know. So obviously point C is at 16, point C has coordinate 16, 4, right? Our equation is y is equal to tan theta x minus 4.9 x squared on u squared cos squared theta, right? So if I sub in the points 16 and 4, I'm going to get my first equation, which is 4 is equal to 16 tan theta minus 4.9 times 16 squared on u squared cos squared theta. Cool. Okay, that's the first bit. Now, so that's going to be our first equation. Okay, so now we use this second bit here, the second idea, the idea of it joining the part of the car, part of the rear wheels of the car joining up smoothly with the second ramp, right? So again, it looked a bit like this, and then you have point C here, right? Point C, and then this was the ramp, and it was angled at 10 degrees. Okay, so what we have to take into account here is obviously the path of the car, this equation here is a parabola, right? So it describes a parabola, right? And we can see that at this point, like right at the end of the flight, when the car finally ends up back on the ramp, we see it joins up very smoothly to this ramp, right? So the ramp and the path of the car need to have the same gradient, right? So what is the gradient of the ramp? How do we find that out? Well, gradient is rise over run. So rise over run is equal to, well, rise over run is the same as opposite over adjacent, which is just the tan ratio, right? So tan of whatever angle this is rise over run. So tan of 10 degrees, right? But is this completely correct though? Because we obviously know what the diagram looks like. Again, I might go back up to show you what it looks like, right? We see that this angle here is 10 degrees, so we know that the gradient is tan of 10, but is it just tan of 10? Because we can see that obviously this line is facing the other way, right? It has a negative gradient, obviously. You can see that whatever this ramp is, if this ramp was to be, represented by the equation of a line, it would have a negative gradient, which is why the answer to the gradient of the ramp is not really tan of 10, it's actually negative tan of 10 degrees, right? So we just have to use this piece of information here. So the angle of the ramp, so the gradient of the ramp, so m ramp would be minus tan of 10 degrees. Okay, how do we find the gradient of the path? This is actually not that hard either, because we already have the equation y in terms of x for the path, right? All we have to do is find dy dx, right? Specifically, we want to find dy on dx when x is equal to 16, right? We want to find what the gradient of the path is at that point where it lands at this point C here, 16.4, right? That's what we want to do. Okay, so let's go ahead and do that. If I take the derivative of this thing here with respect to x, well, then I just have tan theta, because remember we treat every other variable as a constant. So I just end up having tan theta. And then this bit here, 2 times 4.9, just using the power rule here, 2 times 4.9 will be 9.8 x on u squared cos squared theta. Okay, so I end up having that. I guess I can replace the x straight away, get rid of this x here and replace it with the 16. Okay, cool. So we have that. So that's what we have right now. We can equate these two sides. So remember, the gradient of the ramp and the gradient of the path at the point where x equals 16, they're equal. right? So I can equate these two sides. So minus tan of 10 degrees is equal to tan of theta minus 9.8 times 16 over u squared cos squared theta. And that makes our second equation. And as you can see, we only have two variables in both equations, in the first equation and the second equation, and we only need two variables to solve a problem like this, right? So yeah, we just sub this into, we go into the CAS, we put it into, you hit menu 371, you solve a system of equations, and you solve for both u and theta, but just make sure, just to make sure you're taking into account that theta must be, between 90 and 0 degrees, right? Because obviously you can see that it's a positive angle. So yeah, solve it with that restriction and you should get the answers. Theta is equal to 34.07154998 and u is equal to 16.371132. Well, we wanted the answer for theta in degrees, correct to the nearest degree. Therefore, answer would be theta is equal to 34 degrees, and we wanted u to one decimal place, so the initial velocity is 16.4 meters per second, and that's our answer. Okay, cool. So far so good. So now what happens is we go, so we sort of finished with this vector calculus parametric equation portion of it. What we're doing now is we're talking about how we're just talking about acceleration, motion in rectilinear motion. So motion in one direction. Yeah. So what we have to do is, we have to use the concepts of variable acceleration and the concepts of constant acceleration in order to solve a question like this. Okay. So what are we told, right? We're told that our acceleration is equal to 60 on v, and v, so where v is speed and s is meters. Okay, and you want to show that v in terms of s, so you want to show that the velocity in terms of s is given by this equation up here, right? So you want to get from this bit here to that bit there. How do we do that? Well, we know that with our variable acceleration formulas, we know that we can write our acceleration as v times dv on ds, right? So this is one of our variable acceleration formulas. So once we do that, we can write that a is v dv on ds is equal to 60 on v, and now we end up trying to solve this question. So we'll multiply both sides by v. So what I can do is I want to get rid of the v on this side. So I can actually what I'll do is I'll probably multiply this whole thing by 1 over v, right? Right? So then dv on ds here will give me 60 on v squared. Then obviously we have the top variable as the variable in this equation, so what we have to do is we have to flip it. So instead of dv on ds, we have ds on dv is equal to v squared on 60. Once we do that, we can just integrate. Once we integrate, we're going to get s is equal to, so what I'm just doing is I'm integrating both sides with respect to dv. Right, so then once I do that, s is going to be v cubed on 180 plus c. But since, c is equal to 0 when v is equal to 0, this c just, s is equal to 0 when v is equal to 0. What happens is the c just becomes 0, right? That's it. So that's pretty much it. Therefore, I'm going to get s is equal to v cubed on 180, and then just rearranging for v, multiply both sides by 180. I'm going to get v cubed is equal to 180s, then take the cube root of both sides. Therefore, v is equal to 180s to the power of 1 on 3. And yeah, we've shown what we want to show, so that's our answer. Finally, part E, we want to, one is just, it tells us a bit of a story about how the car leaves at this point A. So if I just go back to the diagram, just to, help you remember what's happening here. This is the point A. The point W lies between A and B, right? So that's A, W, and B are the points before it reaches this point O on the ramp, right? So I'll just sort of reproduce that, that part of the diagram at least. So we have A, then W somewhere in the middle, and then B here. So A, W, and B, and they're all joined up. Okay, so they're all on a flat part of the ramp. Yeah. So now, what are we trying to do here? Well, we are told that after this car leaves at point A, it accelerates to reach a speed of 20 meters per second at point B. Okay? But then we're told that if the sun is called off, the car immediately brakes and will reduce its speed at a rate of 9 meters per second squared. So we know that, so what I guess the information we can tell from here so far, we have these two pieces of information, but we know that the acceleration is constant because it reduces the speed at a rate of 9 meters per second squared, right? So acceleration is constant at negative 9, yeah, so just negative 9 meters per second squared. Cool. We also know that it's only safe to call off the stunt if the car can come to rest at or before point B. And point W is supposedly the furthest point along this section AB where the stunt can be called off. Okay, so what we want to do is we want to find out how far is point W from point B. So how do we really go about doing that? First of all, what we can do is we can find the distance from A to B, right? So that's going to be helpful for later on finding out where this point W really lies. So the distance of A to B, right? How can we go about doing that? Well, we already have an equation, don't we? From the previous question up there. We know that V is equal to the cube root of 180s, right? So V is equal to 180s to the power of 1 on 3. Okay? And we're told that if we don't stop, right? If we don't stop and we reach point B, right? Then we will have reached the speed of 20 meters per second, right? So we can go ahead and try and solve that to find out how long it is between A and B. Like, what is that distance, right? Because obviously we have an equation in terms of V and S, which is exactly what we need. So 20 is equal to 180 s to the power 1 on 3. 20 to the power of 3 is going to be, if I take both sides to the power of 3, I'm going to get 1,000 is equal to 180s. Obviously you can do this bit on the calculator, but yep, I'm just going to finish it off now. 180s, sorry, no s here now. This cancels out. 800 on 18 becomes 400 on 9. So we know that this distance from A to B right now, that's going to be 400 on 9 meters. Okay? So how do we find how far point W is from point B? Well, we're probably going to have to use some sort of constant acceleration formulas. One of the constant acceleration formulas. And I'll tell you the one we're going to use this time. The best one to use in this case is actually V squared is equal to U squared plus 2AS. Why is that? Well, think about what's happening here, right? If the car was going to stop at W, if it was going to like start braking at W and then finally come to a complete stop at B, then my velocity at B would equal to 0, and my velocity at W is something I don't know I don't know right now, right? So my initial velocity at W is an unknown, but my velocity at B, I know that for sure. My final velocity will be 0. Okay? But actually, do we really not know what the velocity at W is? Well, we can probably use the fact that this whole distance from A to B is 409 to sort of come to an understanding as to what this as to what our velocity at W is going to be, right? Because at the end of the day, what we want to find is this S term here, right? So our equation previously, V is equal to 180 times S to the power 1 on 3, right? What if we were trying to just use this equation here? What if we try to use this equation here to find out what this initial velocity at W was, right? Well, if this whole distance from A to B was described as 409, right? Let's take this S thing here. Because what we want to find is the distance from W to B. let's take this s term here and call this distance from W to B s, okay? Therefore, if that distance is s, then the distance from A to W must be 400 and over 9 minus s. So if that's the case, then what I can do here is I can say my initial velocity, right? I can say my initial velocity that I don't know what it is right now, given this equation here, is equal to 180 times the distance times s, which is the distance that it has already traveled, which in this case, if you have gone from A to W, is 409 minus s. 409 minus s to the power of 1 on 3. Okay, just be aware of what I'm doing here. I'm using a variable acceleration formula, right? So I'm using so we solved this previously to get this equation here. We used the variable acceleration formula to arrive at that point here. But what's happening here is this 180s to the power 1 on 3, that equation describes what is happening from A to W, right? Because I know at point W is when I start braking in, that's when this whole motion turns into a constant acceleration problem. So we don't have to, so from the point of A to W, we don't have to worry about any sort of constant acceleration. We don't have to worry about mixing the two up. Okay? So anyways, that's the distance I've traveled. If I'm calling this distance here between W and B, if I'm calling that S, then the distance between A and W is 409 minus S. Therefore, if we want to find the initial velocity using the equation we used in the previous question, this 180s to the power 1 on 3, I can sub in that distance, which is in this case 409 minus s. So 180 times 409 minus s to the power 1 on 3. And that's all I have to do for the initial velocity. So the final velocity obviously is 0. The initial velocity is what I had before, 180 times 400 on 9 minus s to the power 1 on 3 plus 2 times a, we know a is negative 9, and s is what we're trying to find, right? And then, we go in the calculator and we try solving this. Having solved this in the calculator, we're going to get s is equal to 16.362797, blah, blah, blah. We want the answer to 1 decimal place, so we just round s up to 16.4. 16.4 meters. Yep, and that's about it, really. That's this whole question done. Well, this was a sort of a difficult question, but I guess this whole problem was. But as you can see, most of it could be solved with just understanding some of the basic ideas that were presented in the problem and are introduced from like your basic kinematics formulas. As with this one as well, wasn't really that hard. Just taking into account some of the keywords and using the hints that VCAA has provided you in order to solve the problem. Okay, so that's about it for this question. I'll see you guys in the next video. Thank you.